find the derivative of the constant function here. We'll use the definition. Limit, we could use, we'll use this one, delta x goes to 0. F of x plus delta x minus f of x over x. Okay, for our function, it's a constant function, so we have this. We have f of x. See, in this case, our f of x is actually a c. So f of x plus delta x is also a c. So we have c minus c over delta x. Well, that's just, we never even get to finding the limit, in the sense that we have this already, which is 0. So that's our first result. That derivative of the constant function is a 0. Now, this one involves using the binomial expansion, which I've written down here. Need this result to prove this. And this is for rational values of n. Prove it for the real values. So the point is that when you set up your derivative, you're going to have this limit. Delta x is heading to 0, and you have f of x plus delta x. Oops, minus f of x or delta x. And what you'll do is you'll put in this expression I have up here. This is the expression for x plus delta x to the nth power. So we'll have all of that. I'll just I'll kind of cheat here a little bit. I don't want to rewrite all this. So we have all of that, and then we're going to minus. So let me take a step back here. Let's see. This. Okay. All right. I just want to make this a little easier. So in other words, our limit, we have a set. So we have a limit delta x, that's 0. F of x plus delta x minus f of x over delta x. That gives us this limit delta x plus 0. You have all of this. Yeah, I'm going to just kind of remove this. We have all of that minus x at the end, all over delta x. So I'm just kind of squeezing this in here to save space. And that gives you this limit. Your x at the ends cancel. And notice that the delta x divides out of each one of these terms up here. So in the first term, I have n x to the n minus 1. And then in these other terms, we'll lower our power of delta x by 1 in each case. So the first term will be, I'll just write the first one, n minus 1 over 2, x to the n minus 2, and then you'll have a delta x. And then you'll have the next term, which will also have a delta x. And all these terms will have delta x's. So the point is that when delta x heads to 0, all of this ends up as n x to the n minus 1, like that. So a nice formula for a power function. And what does this mean? It means we don't have to use definition so far. That's what it's telling us. We're not going to have to use a definition on these expressions. Okay, now here's another one. I'm not going to go through the proof of this. I don't want to bore you with it, those details, but you can certainly throw in this constant and prove this one for yourself. It's not that difficult to do. So let's scroll down here. this one, just the author mentions this one is kind of special, fairly obvious. Slope of this line, that this is a line, y equals x. Everybody knows the slope of that, right? The slope is 1. Well, if you differentiate this using the power rule, you would get a 1. And that's all that this is saying. And that slope is the same. Okay, it happens to be constant for this line. The slope is constant for that line. Okay, now, again, these can be proved using the limit definition, just by putting it together. Fairly simple. These two can also be used, but you'll need to use a little bit of trigonometry. You'll have to work with the cosine of a sum and sine of a sum and difference. So basically the sine of the sum, and work with that and reduce it. A little bit of trig there, but not too bad. And you'll get these two results, a couple more derivatives of some important functions, sine and cosine. So we no longer would have to use the definition to work with those two. Okay. Now let's go through a few quick examples here. So derivatives of each of these, we're going to have, okay, so this one. It's a constant times x, so we know that our derivative f prime would just be that constant times the derivative of x, which is a 1. So it's just a 5. Derivative of this function is the sum of two functions. So the derivative would be the sum of these two derivatives. This is a constant, so its derivative is a 0. Derivative of a sine is a cosine. Okay, and there's your result. Just write that as cosine of x. So you now have the derivative function. G prime. This is a sum of several terms. They're all power functions. Here's a constant function here. So the derivative is the sum of each of the individual derivatives of each term. So here I would have, using power rule, 3x squared. Here I'd have 3 times 2x. Okay, so that's a constant times a power function. Minus 3 times a 1, derivative of x is 1. And then plus a 0. So usually you can write that all in one step, but I thought I would explain a little bit about where the numbers are coming from. Let's do h prime here. So 5 times the cosine plus constant 3 times the derivative of cosine, which is a negative sign. So you can rewrite that as minus 5 cosine of x minus 3 sine of x. And okay, next one. Okay, next one, notice we're using our new rules. H prime, be a negative 3 times a 1, its derivative of x is 1, times the constant, it's just a constant times that derivative. So constant times the derivative of sine, which is a cosine. So you can write this as negative 3 plus 4 cosine of x. And this one, I'd write it this way first, because we haven't seen any forms like this for differentiation. But when we put it in this form, as long as this is an integer, we can use our rule, power rule. So I wrote it this way, and now I have this as 3 times negative 2x, 3. So that's a negative 6, and you'll write it over x to the third, like that. So just put it back into that form. Okay, so this rule that we saw up here, back up in here, this is actually good for, notice n is a rational number. Okay, so I haven't done for all real numbers, but this proof does hold for rational numbers. And that's because this expansion here is actually good for any value of n, whether n is, it's good for all rational n. Okay. Now to prove it otherwise, we'll take a little bit more. We're not going to do that right now. So we're going use average zone. And now we have another concept here, the average rate of change. I think we're going to include the rest of these problems on another video. So quits for this one, look for the next video.